I am going to be talking to you today about estimating non-viable models for machine learning projects. The outline for the talk is as follows. So I will spend some time stating what the problem is, what we're trying to do here, and justifying why this is something that needs to be done, including embedding that in the existing literature. I'll be talking more about the specifics of the problem definition. So because in this case, we are looking to estimate what a model needs to be before it's built. So we have to talk about what the data that will be available at that point. So this is effectively one of the core parts is deriving a cost matrix from business criteria. I'll be then exploring two methods of attempting to do this minimum viable estimation. One is analytically, so to determine, what can we determine analytically a priori about what the performance needs to be, and then we'll turn to a numerical technique to try and estimate those the types of metrics that aren't amenable to analytical analysis. And then finally, one of the benefits of the numerical approach is that we can then conduct a simulation studies on the problem complexity for a range of different business criteria. So as stated previously, the core idea is we want to be able to estimate how a model will need to perform in order for it to be viable for a given business problem. And the reason why this is necessary is because the current general approach that will be used in the justification of any machine learning project involves two components. Typically, there will be some statement about the size of the problem, i.e., for example, this problem, fraud costs us $5 million a year, for example, and that a reasonable percentage improvement would justify the project investment. So say a 1% reduction is a significant amount of money that will cover the project costs. That is by far and above the most common way that that machine learning projects are justified. But as a sort of a supplement to that, there's a process whereby someone with experience in building models, statistician, data scientist, engineer, will have conducted an investigation to say there's sufficient data at the right point in time. We understand what action will be taken on the basis of that machine learning model, and this appears to be amenable to machine learning. The problem with this is that in many situations, it is possible to build a machine learning model that will be better than random, in fact, often a quite reasonable model, but it still won't provide sufficient financial return. And there are a number of reasons for this, largely due to that in the real world, most situations are highly imbalanced. So you've got, for a very, very low base rate of the event that you're trying to predict. So take the fraud example I started with before. Fraud, most financial transactions are not fraudulent. So you're searching for a 1 in 1,000, 1 in 10,000, 1 in 100,000 event. And that means that the benefits of predicting the true positives tend to be overwhelmed by the costs of making your false positives. There are other scenarios where, say, the costs and benefits are roughly symmetrical, or even the cost of making a false positive is higher than the benefit of true positive. So even then, even if it's not a low base rate problem, that can still make it very, very difficult to come up with a viable machine learning model. So the historical context for this is there is a significant body of literature that looks at how you can optimize a machine learning model that takes into consideration these cost and benefit considerations. So the Elkin paper from 2001 on cost-sensitive learning summarizes the literature up to that point, and it's still a very, very good summary of the core problem and sets a lot of the groundwork that I'll be talking about. Now, that literature has largely died down, and in a 2016 paper, concluded that really we should focus on optimizing the model using standard metrics and typically making a well-calibrated probability distribution, and then optimize the threshold through a cost matrix analysis. So you perform the cost-benefit analysis separate from the model fitting process, and this has become something of a de facto standard. However, note that in all of this, the discussion is always about either how that you can train the model to be more sensitive of the costs, or given a model, how can you determine the threshold that optimizes the cost benefit outcomes? It's not about how you can a priori determine how likely it is a model you're going to develop will satisfy your ROI or return constraints. So the cost matrix analysis, sorry, I should state here, for the purposes of this paper and presentation, I'm going to be restricting the discussion to binary classification. You can, in many multi-class classification situations, you could adapt much of what I'm talking about here, but work on, say, regression and time series would be altogether different. So in this paper, I am focused purely on binary classification. So a cost benefit matrix looks like the following. It's a corollary to the common confusion matrix in binary classification, where the two rows here we have depict whether we've predicted an event to be negative or predicted it to be positive. And the columns determine whether the observed event actually was negative or actually was positive. So typically it's the true positives here in the bottom right-hand corner that are the things that you're trying to realize, i.e. predict the, say, fraud event correctly and then realize the benefit of making that prediction. And the common cost scenario is that you've predicted something to be positive, but actually it was a negative. So that's your commonly called false positive, and that will incur some kind of cost. Now that cost may just simply be the cost of taking an action, but it could also be the cost of the action plus some additional costings as well. For example, a customer choosing to leave your service because they're unhappy about the action you take, or so their transaction was held up because it was thought to be fraudulent. Now, I should note here, I'm going to be following the Elkin approach of focusing only on the false positives and true positives, because in most real world scenarios, the difference you're imposing from the status quo is only when your model's predicting positive. So you leave all transactions that were not predicted to be fraudulent alone, so they have no impact on the cost benefit analysis. It's only those that you act on, the true positives and false positives, that do. You can, of course, flip this around and say we're going to take action on the negatives, in which case, without loss of generality, all of the analysis I'll show you will be flipping to focusing on the negative events. And in fact, you could also take action on both of those at either end of the spectrum, and in which case it would be effectively a doubling of the analysis I'm going to be showing you. But there's no loss of generality if we focus just on the true positives, false positives. So in order to investigate a business problem in advance, we're going to be setting the following parameters. We need to have some sense of what the number of cases that has to be investigated per unit time. And this is going to be related to the next two parameters. We need to know what the base rate of the phenomena is. So for example, we might investigate 1 million fraud events per year, for example, and there might be usually it's sort of 0.1% fraud rate, for example. And then we need some kind of estimate of the minimum required ROI. So effectively, how much money does this model need to save us or make in order to justify the project and to consider moving forward? So typically the value M here will be tied to the value N. We need to have let a significant proportion of time elapse to realize that benefit. So those two things will be dependent upon each other. And the final two values here, the benefit of making and acting on a correct prediction and the cost of acting on an incorrect prediction, of those things that we discussed previously on the cost matrix analysis. So with those things set in place, we can derive some very, very simple formulas to begin with. So it's fairly straightforward to see that the number of true positives times the benefit of those true positives minus the cost of making the false positive predictions has to be greater than or equal to our desired ROI. That's very straightforward. We can then rearrange that to find expressions for the number of true positives and false positives, but you'll note that they're each dependent upon each other. So there's a relationship between these two that that in a sense can't be analytically reduced. We can also then introduce the number of number of cases and the base rate to come up with expressions for what we know the true positive rate and the false positive rate are going to have to be. But again, they both depend on the number of true positives and false positives, so we can't reduce that further for the moment. Now, there are a wide array of other metrics that machine learning practitioners will look at when building models. I'm going to focus on the precision, which is one of the more common and the one that is most amenable to the kind of analysis I'm going to show you. And the precision effectively says when we make a prediction and we act on it, how often we write. So it's commonly expressed as the number of true positives over the number of true positives plus the false positives. And so we're able to actually come up with an expression from that using the formulas on the previous page as to what the precision needs to be at that point where we're achieving our minimum ROI. Note, however, that the number of true positives is expressed in this formula, so we can't reduce that further. However, we can make a simplifying assumption and say, well, let's now investigate, rather than at the point where we make sufficient money, let's just look at the break-even point where effectively the model is not costing us anything. And that gives us at least a lower bound. We know that the precision has to be greater than that break-even point. Now, in order to sort of understand what we're looking at here and to do further investigation, we plotted that in a sort of a schematic diagram to understand what's happening. So this is somewhat similar to an ROC plot, except that the axes here are not normalized by the total number of cases, positives or negatives. So we're looking at the x-axis on the total number of false positives made. In this case, we're thinking about the predictions. And on the y-axis, we're looking at the number of true positives made. Now, we have bounds on what those can be. We know that the total number of true positives can never be greater than the population times the base rate. And of course, we've got the inverse probability times the population gives us the total number of false positives. Then we show on this plot a couple of lines here. The red line shows us that the formula we showed previously, the absolute lower bounds here on the precision, but rearranged so that we're expressing the true positives as a function of the number of false positives, which we're expressing up here with the red line. The black diagonal line shows us what the values would need to be to achieve our minimum ROI requirement. And sorry, I should note quickly, there's a typo in this in the plot here. That minus there should be a plus. So now this line here is and you can effectively read off what's happening here. The benefit by the true positives has to be outweigh both the desired ROI and the costs of the false positives. So one of the nice things about looking at it in this geometric representation is we can now say, well, interestingly, all of the points above this black diagonal line describe potential model outcomes that would satisfy our business constraints, and the entire rectangle describes all of the possible model outcome results. So we've actually got a geometric representation of effectively the ratio between desired model outcome results versus all possible model outcome results. And you'll notice that when we derive expressions for the dimensions of this triangle, we've actually managed to eradicate all of those, the true positives and false positives from the expression. So we can now, that gives us a method for effectively estimating how simple a potential machine learning project is simply using the business criteria we've been given. And that's the formula we've derived here. So just to restate, the idea here is we can take two business problems defined by those raw business criteria, and this formula tells us how simple they are, and we can compare them against each other because it's only considering basically what is the ratio of potential of models that satisfy our criteria versus models, the total space of possible models. So that's the first major outcome of the paper, a general purpose simplicity metric for models basically just from the business criteria. However, we haven't managed to derive any of the standard machine learning metrics analytically from those raw criteria. So I'll now turn to the second part of the paper, which is on numerical estimation. So we want to ask, how would we go about coming up with reasonable estimates of standard metrics like say area under the curve or precision and recall, Matthew's correlation coefficient, many of the others, given a numerical technique. So one reasonable place to start is to think about the ROC curve, because it's a standard method of analyzing binary classification models, and it allows you to do this without considering the nature, without specifically taking into consideration the imbalance of the classes. So you can compare ROC plots even if the underlying business criteria are quite different. Now, luckily, the ROC plot has some really simple characteristics that are amenable to simulation. Basically, it's a monotonically increasing function from 0 to 1. It has to give values over a domain of all real valued numbers between 0 and 1, and it has to pass through the points 0, 0, and 1, 1. So fairly simple criteria. And what that means is that we can derive an expression that allows us to simulate functions that have these properties. So the approach that we've taken is to basically take a mixture model of two different functions that satisfy that criteria. The simplest, of course, is just a pure linear model. So I should mention the alpha constant here is the mixing parameter. So we've got a mixture of this even powered polynomial and this linear function here. Yeah, both of those functions independently satisfy the criteria, and so effectively the linear function flattens the curve, and the polynomial function allows us to both just define the curvature and how close it moves towards the y-axis. So here are some example plots that you can generate by basically varying the values of alpha and beta. We can simulate different potential ROC plots and use this. Effectively, the approach we use is then by simulating these ROC plots, then testing whether there is a point on the curve that satisfies the business criteria we've been given, and then choosing the ROC plot that has the lowest AUC that satisfies those criteria. So again, it's a simulation technique that allows us to say, okay, what AUC value, at least do we have a sense that we're going to have to achieve in order to satisfy the business constraints. So one of the advantages of taking this approach, this simulation approach, is that we're now able to we can now actually perform simulations over a wide array of potential business problems. So by which I mean, we want to say, can we gain insights into what the landscape of business of problem complexity is, irrespective of the fundamental details other than the criteria we've been given. So we're going to conduct a simulation over a set of realistic values for potential cases. So we've explored sort of 10,000 to 10 million, and because we found the results were more or less the same over those ranges, for the rest of the simulations we've used 1 million as the value for n. The base rate is something that does vary a lot between business situations. So in the simulation studies we've done here, we've taken 10 to the -1 to 10 to the -5 as the values that we've simulated over. And then the economic considerations we've collapsed into two different metrics that effectively capture the fundamentals of many different business problems. So the cost and the benefit we've collapsed into a cost-benefit ratio. So basically, for example, a value of 1 means that the benefit of every true positive is equivalent to the cost of every false positive. Versus sort of 10 to the -4 means that the cost is sort of 1 in 1/10,000th of the benefit of a true positive. So because that's the range of what we see as generally realistic values. And then the final metric we've generated is the benefit to total ROI ratio. So this effectively means if you need to achieve $1 million so no, let's go with something simpler. $1 million worth of value, and each true positive realizes $100,000. You know, you can calculate that benefit to ROI ratio as 1 in 10. And so that allows us to, by simulating over a range of values for those, we can then look at how the AUC value of the lowest AUC value that satisfies the criteria varies across those metrics. So for the sake of visualization, what we've done is a large scale simulation across a wide array of values for all of those. And then what we've plotted is the AUC, the minimum AUC that achieved that by each of the different metrics we're looking at. So the top one here is simply by base rate. So you can say, you know, when the base rate is sort of 10 to the minus 1 or 1 in 10, basically it's relatively, the AUC, mean AUC is relatively low, sort of, you know, very just slightly above random. So these are easy problems to solve on average. And I should mention, sorry, the gray shows us the 25 to 75% boundaries on that. So what that tells us is that 50% of the values in the simulation lay between those. So you'll note that the boundaries get squeezed at either end. So down here, most problems are very easy to solve. As the base rate starts to drop and so the events become rarer, both the problem in general gets harder, but also there's more diversity. So these median base rates, when the base rates are in these kind of ranges, there's a greater dependence on the other aspects of the problem for what the minimum viable model is going to be. Whereas here at the other end of the spectrum, when the base rate is extremely low, it almost doesn't matter what the other considerations of the business problem are. It's a really hard problem, and you're going to need a model that's approaching perfection. Similarly, we looked at the AUC for the cost of benefit ratio. So effectively, unsurprisingly, when the cost of benefit ratio is very low, i.e., the benefits, the value of the benefits vastly outweigh the costs, they're generally easier problems, and it gently increases. But we'll note that there's a reasonable spread across all of those values. And then finally, we also looked at it versus total ROI ratio. And again, this is probably the least interesting plot here, but you'll notice that it's, you know, when in situations where a few true positives can basically achieve your ROI, they're relatively easy problems. As you need to identify more and more true positives, the problem gets increasingly harder. Now, to understand some of these relationships a bit deeper, we then conducted we plotted that two of these on a 3D plot. So basically looking interaction between the base rate and the cost benefit ratio, which you'll note are these two ones here at the top, to understand how they relate to each other. So again, looking at AUC on the y-axis or z-axis in this case. So what we'll note is, as observed before, really, really low base rates. What we see is these are hard problems, and it doesn't seem to be sensitive to the cost-benefit ratio at all at this spectrum. As the base rate starts to increase, what we see is across the board, the problem gets easier, although it's somewhat mitigated by the cost benefit ratio. So effectively higher cost benefit ratios mean that process takes a little bit longer. And interestingly, so the problem we see, high cost benefit ratios in general make the problem higher. However, at the very, very low end, they almost totally mitigate that base rate problem. So you'll note there's a very flat area here. Very low cost benefit ratios means that it doesn't matter so much what the base rate is in this kind of reasonable range here. So some simulation conclusions. I'm effectively just restating some of the things that I said here. That we see that very low base rates can generate intractable problems that are likely to be extremely difficult to solve, so requiring AUCs of approximately 1.0. Problems are invariably hard when the cost benefit ratio is higher, but as we saw, as the base rate increases, we see a general weakening of the effects of the cost benefit ratio, and likewise at very low cost benefit ratios, the impact of the base rate is almost entirely mitigated. So I guess overall paper conclusions, we've investigated analytical and numerical methods for estimating minimum required model performance. We provided a novel metric for estimating the problem simplicity that you can use purely on the basis of the statement of the business problem, and that you could compare the requirements of two business problems that can potentially be used for, say, ranking projects in order of priority. We've explored the landscape of business complexity through simulation, and the code for both, we've generated a package that allows you to sort of generate these simulated AUCs and the simplicity in a web application, as well as you can see the simulation studies code on the GitHub repository. So thank you for your time. Any questions?